All right. PhD, we can start presenting.
Do you want to put it in full screen mode? Or...
Oh, wrong screen then, my bad.
Oh, you're good.
Stop sharing. And this one. There we go. Can you guys see the screen?
Yeah, that looks good.
All right.
Should we start?
Yeah, we can start.
Okay. So good afternoon, everyone. My name is Angelica, and my team is composed of Jamari and Kim and myself. Our final project proposal is based on IoT, or the Internet of Things, and smart grids. We hope you enjoy our presentation. Next slide. Today, besides giving you guys a little introduction of what our project is, I will also be discussing the motivation, meaning the name of the topic as well as the goal of our project. Then I will pass it on to Jamari, who will discuss the significance, the problem, and the objectives of our literature paper. And lastly, we will have Kim discuss the current literature works that discuss the problem, as well as a brief overview of our schedule and our references. Next slide. Now, let us say that you as a consumer, you're in your home and you notice that your phone is dying. Now, I'm assuming that most of us have smartphones, and smartphones today have fast charging technology. So let's say your phone is at 20% and you plan on plugging it in for about 30 minutes, get it up to, I don't know, let's say 60%. And as you're about to plug it in, you notice that it's peak time, meaning that the cost for electricity is at its highest at the moment. Alternatively, you remember that you have a portable battery. So you decide that you will plug in your phone to the portable battery to wait out the peak time so as to reduce your electricity consumption. This same approach could potentially be applied to electric vehicles as well. Do any of you own an electric vehicle, or do you drive someone else's electric vehicle? Yes, no. No, that's okay. For the purpose of the example, you don't really need to. However, if you do, just replace the phone in the previous example with your electric vehicle. And this introduces our topic. Our topic is PHEV and VEB substations with smart monitoring and load balancing. So just so we are all on the same page, PHEV stands for plug-in hybrid electric vehicles, and BEV stands for battery electric vehicles. And the main difference between the two is that the plug-in hybrid is half electric, half gas fueled, while the battery electric is an all-electric vehicle that has to be plugged in to charge. What we mean with our topic is that, going back to our previous analogy, we would like to know if it would be possible for an electric car user to offset peak demand by using charging stations with smart monitoring. Meaning, if the charging stations are able to take data about the car, store the data, analyze whenever the user comes in with their car and at what time, and possibly predict future arrival times for the car so that there is power available to charge the car, therefore resulting in the load being balanced for the charging station. Now, the goal for our project is to find answers to the following questions. Our first question is, can we predict peak times of use for charging stations? Our second question is it possible to support the substation to compensate for peak demand? Going back to our previous analogy, is it possible to maybe have external batteries connected to charging stations to offset peak demand? And the third question, giving whatever solution to a problem that we find, is the solution flexible enough for both residential and commercial situations? Now I will pass it on to Jamari, who will discuss significance.
Thank you, Angelica. So we need to understand the significance of this problem. So it's all nice that Angelica has found all these different methods to solve the EV problem, but is there even a point to researching all of this? What's the significance of researching EV and smart monitoring and UPS substation backups if there is no demand for this. So let's just take some numbers, and I want to give you guys a general idea of what the EV market will be in the next few years. So of course, the project is going to encompass both consumer and commercial applications. So this includes residential and fleets like Amazon, Volkswagen, Ford, the Ford Transit vans. So just to throw out some numbers, in 2019 alone, the global electric vehicles in operation, so this is people who are driving vehicles, was around 7.2 million units, right? So it's a decent amount. So just to give some numbers, 7.2 million units globally is around 7.8% of the total vehicles being produced. So the total vehicles produced will be 7.8% electric vehicles, and the rest will be gas or other technologies like the fuel cell for the Toyota Mirai that Toyota makes. Now, there are some prediction models that range all the way from today's date to 2035, 2040, and 2050. And I do have one aggressive model that predicts the total number of vehicles. Does anybody in the audience would like to give us a number that they can guess how many electric vehicles will be in operation in 2050? Any guesses at all?
I would guess 90% of the total vehicles.
90% is a pretty aggressive model. Do you have like a quantity that you can guess? Probably, maybe in the millions, maybe higher.
I could guess, I don't know, like 75 million.
Okay, that's actually a low prediction model. So in 2050, the actual production units is around 247 million in 2050. Still, that's nothing compared to the actual gas vehicles being used today. So, I mean, who knows how the market will change in the next few years. So just to give you guys some idea, 247 million by 2050. So it's a decent amount. Now, moving on, there's going to be a problem. 247 million vehicles that are electric vehicle on the road is going to give us a lot of problems. And like, we need to understand why would this be an issue? If we can understand the issue, we can then find solutions to our problems. So, of course, there's going to be increased demand on the electric grid. It's a given. There's more people on the road, there's more demand. Now, because there's more people on the road, the peak demand, which essentially means that the price of electricity for a given amount of time is much, much higher than the average. The peak demand is going to be much greater in interval time. So an estimate would be the peak demand for like the United States is from 12 p.m. So basically noon until around 3. So that's around lunchtime because people, go to lunch, they plug in their vehicle, they eat, and then they go back to work. And then that's pretty much the peak demand, is that little curve right there from 12 to 3 is your peak demand. Now, is there any way we can mitigate this? Yeah, I mean, so for example, Tesla, right? Tesla also has their substation. They have substations at malls, dealerships, at some workplaces if they have a contract with Tesla. But Tesla doesn't do much IoT integration. So we need to find out if we can, implement that into our system. And of course, we're in 2021 right now, and there's still not that many charging stations. The most dense charging station infrastructure is in California. And that's not enough if there's 247 million units in 2050. So just to give an idea, the Super Bowl, right? Super Bowl, I think, is on Monday, Thursday, and Sunday. The Super Bowl peak demand is as follows. So from midnight until noon, there's very, very low usage because everybody's sleeping or, they're getting ready for work, right? And then from noon until 6 p.m. is when the Super Bowl, everybody's watching the Super Bowl. So the electricity is going to be very high. The usage is very high. And then halftime, and then the final moments of the game is from 6 to 8 p.m. So there's actually a curve. It's called a Super Bowl peak curve. From 6 to 8 p.m. is the highest demand. And the charging stations and the electric grid is going to have the highest demand during that point in time. So that's a very good example of what our job is trying to solve is, can we mitigate this peak demand for our substations? And the objectives that we'll be going over is the following. So again, we need to identify the problem areas. We need to search out what issues are we having currently with our substations and what issues can we encounter from the years going forward. Then as a group, we will discuss the methods to charge and optimize our infrastructure. And then we will survey the current implementations, the pros and cons, and the limitations of all these implementations being currently in use today or in development. Then we'll ask ourselves a unique question. Can these proposed solutions actually be turned into a modular piece of an idea, or can these solutions be modular? So if our solution works, then we can scale it down to residential. And if it works there, then we can scale it back up into the commercial sector, which is what Ford and Volkswagen is doing. They don't have an infrastructure yet. So that's why they're starting slow. They're slowly introducing models little by little, all right? And then, of course, we're going to report our findings to you guys so that you guys can have a bit of information on the EV market share in 2050 and how we can introduce new concepts and solutions for this EV problem that's going to happen. It will happen, but we need to find out solutions. So that concludes my part of the proposal, and I'll now pass it on to Kim.
Thank you. Well, as discussed, electric vehicle integration faces increasing load demand issues. In response, studies and literature analyze the problem in order to develop solutions involving various approaches to load management. First, we have the probabilistic model. Factors such as battery capacity, distance traveled per day, and entrance time to charging stations are all probabilistic. This therefore implies the need for analysis of probabilistic models for electric vehicle charging to more completely understand this issue that we're facing. While this is a seemingly mundane mathematical approach, new optimization with these techniques could optimize the smart grid in preparation for the increasing popularity of electric vehicles. Next, we have smart management, and current works here aim to study smart management systems that utilize IoT technology to reduce the effect of peak load time. The daily required energy of PHEVs can be calculated based on randomly determined models of electric vehicle owners' behavior. Additionally, active and reactive power management would be performed for energy loss reduction. Basically, the system archives a history of vehicles that have entered a given charging substation to process load demand more intelligently. This information can be applied to a realistic distribution network where vehicles' active history, it can be utilized for future charging. Next, we have V2G technology. The integration of plug-in electric vehicles and battery-powered electric vehicles into the smart grid is another topic that's currently being studied. Vehicle to grid, or V2G, is a smart charging technology that's actively being tested. It allows electric cars and substations to communicate through their respective networks. This allows electric vehicles to act as a sort of large mobile battery. This up-and-coming technology is hoped to be integrated into developing smart grids in a variety of ways that aim to reduce demand during peak load times. Last, we have energy sharing frameworks. Energy sharing is another topic currently being explored, as it can be applied to the residential sector as an additional feature of electric vehicles, as again, a sort of mobile battery. This is very similar to V2G technology, but more for residential areas. An energy share system would be able to be performed between the home and the workplace in order to manage peak load times. Overall, the subject of these preliminary works can be analyzed in order to compare and discover a smarter, more efficient, and cleaner systems in the scope of load management and proper integration of PHEVs and BEVs into the smart grid, even making the smart grid a more efficient system. Next slide. Here we have our schedule. We're going to aim to obviously get things done as soon as we can and have everything by our due dates that we have set. Next slide. And then we have our references, which is pretty self-explanatory.
Awesome. Thank you so much, Kim. So are there any questions about our presentation? Any doubts, anything that's unclear? I have my notepad ready to take down those questions.
I had a question. So how do you have any idea how you would go about like identifying So you said you were gonna like when people with their electric cars came to like the charging stations, you were gonna store information about like their car and try to like predict when they like predict their arrival time. Do you have any idea what sort of information you would be storing in order to identify the people and like what the model for predicting the arrival times would look like?
That's a pretty good question. I'll start it off, and if anybody else wants to add, they can. So, for example, the car VIN number. The VIN number has a lot of information. If you look up that VIN number on a website, it can tell you the make, the model, the engine capacity, the current owner, the license plate. It gives you a lot of information. So the VIN number itself is a good way, but of course, that's the physical aspect of the actual car. However, nowadays there's so much technology packed into the cars that it's linked to our phones. So let's say we gotta connect to charge station number 1. I'll take my phone out and connect to it. My phone has all the charge information on that vehicle. And so it will transmit the information to the charge station, and the charge station will record it. Of course, there's a bit of laws and regulation that has to be gone through first, but that's the basic aspect, is taking information from the owner. For example, Tesla does that. Tesla, how do you think they disable fast charging? Your phone is connected to the Tesla, and the Tesla has actually a connection to the telecom towers, which then goes to their cell towers. So if you buy a used Tesla, I guarantee you that they will disable supercharging, the fast charging, unless you pay a additional fee on top of that, because they actually disable it for safety features. Does that answer your question?
Yeah.
Okay, awesome. Any other questions?
I have a question. It goes, you guys talk about it, but just more of a summary. What's the current limitations on the current solutions on the present stations?
Kim, I think that's your question.
Sorry, what do you mean by that? Repeat the question.
What are the kind of limitations that the current solution has? So right now, the charging station, what are they lack of?
I mean, currently there's not much smart integration right now. So a lot of these issues, just like what Jamari was saying, just during peak load times, there is just not, currently it's okay, but as the popularity of electric vehicles rises, charging for these vehicles just won't be able to be supported during peak load times. There just won't be enough. So that's why we need to look at these solutions and figure out how to accommodate these peak load times.
To add to Kimber's, oh, sorry, you were going to say?
I was just going to say thank you for answering the question.
Just to add, so the information that we have seen so far, they're also kind of preliminary solutions. So there are studies made by people who put preliminary solutions onto a research paper. So those solutions are not currently being implemented, but they have found solutions that could be implemented. So our goal is to look at all of those solutions and discuss how they would, how they could be possibly implemented.
And actually, I think like V2 vehicle to grid technology is currently being tested in other countries, like more actively than here, because I don't think there's any like real in community testing of V2G here, but I think in other countries there is some testing of that. So I mean, they're trying to see if that's possible in a larger scale.
Awesome. So I think that's all the time we have. We're just a little bit over time, but that'll conclude our presentation. And thank you so much, guys, for listening. I'll stop the screen sharing, and then the next group can move on up. There we go.
Okay. There is a team of 3. That's us, and then I think there's one more person, right, that is doing solo. Okay. You want to go now? Or you want to go last?
It doesn't matter to me.
Okay. Let's rate one and try. Let's do it now, if you guys agree.
Yeah, perfect. I'm gonna be sharing my screen then and get started. If that's cool.
Yep.
Go ahead.
Okay, perfect. All right, so we all have heard about IoT more or less. What is IoT? Anything and everything that are embedded with sensors, software, and other technologies to connect and exchange data with other devices over the internet is basically IoT, right? So pretty much anything that connects to the internet, right? And with the usage of IoT, the physical world meets the digital world, and thus concepts like smart cities, smart grids, electrical vehicle, and whatnot are coming into reality. Now, as we're talking about smart grids, let's start talking about grids first. What are grids? Basically, the electric grid, transmission lines, substations, transformers, pretty much anything that delivers electricity from the power plants to the homes or businesses, pretty much to the consumers, are grids, right? However, this grid system was innovated and implemented back in 1980, so it is pretty much highly outdated. So in order for us to upgrade this, we can switch over to smart grids. And smart grids allow us for two-way communication between the provider and its consumers, and as well as real-time communication along the transmission lines. Now, some of the problems we're facing with conventional grids are pretty much, they're super old-fashioned and inefficient. Due to the low process time and response time, lack of automated analytics, and poor visibility, issues like blackouts and energy wastage take place. Now, when you talk about blackouts, it's not necessarily people just waiting for their lights or fans to come back on. It's not necessarily that. It could be big problems like power plants stopping, perishable food spoiling, traffic lights going dark, and even credit card transactions stopping, right? So some of the statistics for the economic effects are like a rolling blackout across Silicon Valley totaled about $75 million in losses. In early 2000s, 1 hour outage in Chicago Board of Trade resulted in $20 trillion trade being delayed. The Northeast blackout of 2003 resulted in $6 billion to the region. And also, our grid system is super inefficient. If they were just 5% more efficient, the total energy saved would equal to the fuel and greenhouse gas emissions from 53 millions of cars. Imagine that. So that's how it comes in the IoT, the significance in IoT being implemented in the grids, the smart grids. So what smart grids provide us with is efficient transmission of electricity, quicker restoration after disturbances, reduced operations and management costs, as well as integration of large-scale renewable energy. So, and these are done through different types of methods. So one of the methods are AMI, which pretty much grants the consumers the ability to use electricity more efficiently and detect the problems on consumer level and operate swiftly. We have visualization technology that pretty much enables real-time load monitoring at the utility level. This pretty much grants ability to integrate information from a variety of sources and display different necessary data to different users, whoever needs whatever, right? We have PMU that offers wide area situational awareness to foresee potential blackouts or potential disturbances around the grid. And also it provides real-time information, basically near instantaneous balance of supply and demand at the device level, so that we can prevent any sort of wastage. And now pretty much our goal is to mention some of these IoT devices that are implemented in the smart grids, and like PMU, smart thermostats, smart meters, and battery backups, and how they contribute to solve our current problems with energy wastage and blackouts and cost shortcomings. So if we shift our focus to one of the applications, which is thermostats, and this is performing better than the current technology, the current thermostat many times over. So this technology offers real-time control and monitorization of variables like heating, air conditioning, and ventilation based on weather conditions, building dynamics, like the equipment it's made of, windows count, and whatever is happening within the building, right? So how is it done? it's mostly done by deep learning, supervised and reinforced learning. In terms of machine learning architecture and training, it brings an ability to compute the best of thermostats set points and self-adjusting capabilities, which eventually results in minimum cost of energy, right? And now these systems include communication interfaces to communicate between the sensors. It also has like huge data storage capabilities so that it can record and learn over time. A central control unit that is usually an embedded microcontroller or microprocessor to support the decision-making task after it's learned the mechanisms and the algorithms. This relies on the pricing, the capacity, and the building demands. These optimizations are performed by satisfying the main objectives of saving energy, which eventually minimizes the cost, and maximizing the occupant's comfort, which is the main goal for the smart thermostat system, aka the HVAC system as well. This reinforced learning is optimized is to optimize both energy and thermal comfort, and it is done through different type of functions. One of the functions could be the time step function, which is pretty much a cycle that repeats until the end of schedule and learns all the algorithms and the mechanisms of the building. And after that, data, state, and actions function. So whenever the time step function is running, it collects the data for the weather sensors, the occupants, activities, and the building sensors. And then we have the sliding window concept, which pretty much instead of sorting through the huge amount of data, it just goes through a little bit of data at a time that it records. And towards the end, over time, and this data is monitored and manipulated over time to reach the final goal. And as you can see over here, I put a graph, which is pretty much the energy consumption compared. Our regular thermostat, the RBCs, we have high kilowatts during the different times of the day. However, using the smart thermostat, this black line depicts the total usage, which is much, much lower than the rest of the RBCs. So one of my other teammates are going to take over and go over the other applications.
Next slide, please. To best explain the energy storage system, I will talk about the two incidents that happened for this power grid. The first incident was the blackout in the USA in 2003, whereas the dark area in the circle was a blackout that happened in the northeast region of the USA. So you must wonder what happened. This incident happened because of one simple incident where the power line brushed against the overgrown tree, which created the fault current on the circuit. This blackout that lasted up to 2 days, and it kept around 50 million people in 8 states out of power. It also caused 11 deaths, and it costed up to $6 billion. Who could have thought that the outage can cause deaths, you know? So with what happened, we must wonder what could be better to implement the grid. The answer is to implement a better engineering technology, such as the phase measurement units, PMUs, or the data communications as GPS. However, what if we want to do something better than that? The answer stays in the energy storage system that can be integrated along with the renewable energy. Next slide, please. So the second incident is the outage that happened in Australia in 2017. So for this incident, the power outage wasn't that large because the better IoT technologies that can accurately pinpoint the fault feeder or the lateral, so it can isolate the fault, and more importantly, the energy storage system that located over 600 miles away from the outage location can sense it and kicked in enough power to maintain the grid. at around 7 cycles, which is 0.14 second, which is really fast. So this battery storage located in Hornsdale, Australia. It is from Tesla. It's called Megapack. The battery storage is combined with around 21,000 lithium batteries, and its power is up to 100 megawatts, or the capacity is up to 129 megawatts per hours, which means it can be used for up to an hour to maintain the grid where the other power plants can kick in and keep the grid more reliable. So we can see by utilizing the advanced technology in sensing and communication with the battery storage, the power grid can become smarter to make it more reliable, efficient, resilient, and also cleaner for the better future. Now Oscar will talk about the other applications.
Okay, so according to some of the reports and studies that we have read, they point out that one device that could be where it can be applied, the IoT concept, is the power meters. These are the meters that we see on the side of your home, commercial, industrial areas. They send back power usage once a month for billing purposes. But if we want to really get more information about this device, from these devices, we have to make it into a two-way communication that supports more data. So we start by just replacing these power meters with the smart meters. They will send information back to the company, but more often. So a kilowatt hour, the company can determine with more accuracy the load on the grid. Traditionally, also, customer or the companies rely on customers calling them to let them know about a power outage. But with the smart meters, the company, all they have to do is find out what meters are not sending data back to them. And they can immediately know there is an outage and what extent or what area it is happening, so they can act accordingly. Another type of data that these devices can send is the measurements of voltage and current. So the company can quantify or analyze and get the quality of the power delivered to their customers to foresee some issues as well. Of course, for these devices to send data, the current network have to be upgraded to an advanced metering infrastructure that can support more and more devices at the same time. Another device, next, it's the phasor measuring units. These are installed in distribution centers, distribution power lines, and they measure a different type of things from the current. For example, they can measure the phase angle of the current and voltage sine wave. That data needs to be sent quickly to the power company so it can be compared to the generator's sine wave. It have to be really in sync to make the grid reliable. Any discrepancy, for example, in frequency, it could be a telltale of something going on. And with this unit sending that that type of data more often, they could detect dynamic events as well of what is going on the grid. So this is how pretty much we're gonna divide our workload. We should be ready by week 5 next. And to conclude, to make this communication back and forth between the sensor devices and the power company, they have to be an upgraded network capable of having wireless gateways, servers, storage units. I mean, these devices are going to generate enormous amounts of data that needs to be processed. Some of them have to be analyzed in real time. Others just maybe once a month to get, to find out patterns and consumption. For example, some of this data can end up on a website for you and I to log in and take a look at how much is our power consumption per hour. And even though find out when it's at what time the electricity costs more, for example, so we can plan when to charge our Tesla vehicles, for example. So this is all possible thanks to the application of the IoT devices on the smart grid and the IoT vision, which is have anyone to connect to anything, anytime, anywhere, and get information and act upon that, in real time. Of course, our goal is to learn more about those IoT devices and their impact on the grid and on the quality of our life. This is some of the references we got information from, and that's it. Thank you for listening. Any question?
I have it's not really a question. So, just so that I can completely understand, you guys are doing a literature-based paper based on what exactly? I think I failed to see the exact problem.
Right. So we want to make sure, first, we want to learn all the ITO devices that can be implemented on a regular grid to turn it into a smart grid, to make it more reliable, to predict future. I mean, there is a lot of electronic devices every day connected to the network. There is a lot of new constructions that are going to be a load on the grid. So the companies need to get ready. The current infrastructure does not provide enough data for them to do it reliably and efficiently. So it costs more money to do it now. They're not ready to support all this data. So it takes more time for them to support it. Like my teammates at RID1, it's an old technology. So they have to be an infrastructure that could improve that. So a purpose is to learn about these IoT devices and how they can improve the grid for us. I mean, I hope that
So pretty much, to add on to that, I would like to say basically a literature review of like how substituting our current technology with new technology of like IoT and smart grid implementation, how we can provide better solutions, more efficient, like, you know, cost strategies and energy conservation, and like different applications that are already in motion. If we can regulate those, how we can benefit from that. Pretty much that's our survey topic.
I got it. Thank you.
I have a question. So do you think that with the growing reliance on like technology in the smart grid, do you think it's worth it given possible security risks, like from external sources like hacking and everything?
For at least the smart meters, I feel like it would be possible for hacking. So like while implementing the smart meters, I guess we need to keep in mind like the security is a big issue, because I think what Oscar covered, when the smart meters, they actually send data back and forth, they have access to the building's occupants and like, you know, data of like the household. So more research needs to be done on how to make the smart meters more reliable. But of course, security is going to be needed. It just need a little bit in-depth research on that aspect.
And also to add to that, currently there is no standards about the security of IT devices. Right now it's up to the manufacturer of those devices to try to implement the best security they can. But there's not a guide, there's no guide in the industry that will tell them, okay, this is at least the minimum that you have to do in order to keep it secure. So yes, there are concerns about security, and even if it's small IoT devices, they could be hackable if the companies are not, they don't take security seriously. For example, I've heard of a case where someone hacked into a network through a fish tank thermostat. It's a Wi-Fi thermostat, and they were able to get into the network through that. Why? Because, well, the manufacturer didn't take it seriously, I guess, or there was nothing to guide them to make it more secure. So it have to be addressed. Yes.
Okay, thank you.
So these are some awesome questions, but I think that's all we have. That's all the time we have for this presentation. Thank you so much, guys, for presenting, and I think it's time for the next group or next presenter.
All right, I'll go ahead and share my screen. Can you see the presentation?
Yep.
Okay, perfect. So my name is, let me go ahead and start my own timer. Okay, so my name is Bryce Dare. The project that I'm going to be presenting the proposal for is about the MIDI communication protocol. So you may or may not have heard about MIDI data or the MIDI format, depending on whether or not you have basically any experience with like computer music, which is surprisingly, not really surprisingly, but it's a little bit niche. But I'll give a little bit of background on exactly what that is and what the impact it has on electrical engineering and how that interacts with both musicians and with people who design the electronics that musicians use. So a little bit of background. So back in the 60s and 70s, people who were designing musical instruments were designing a lot more electronic musical instruments, and they were designing analog synthesizers and stuff like that. But as time started to go on, different manufacturers of musical instruments started to make instruments that didn't really make any sound at all. They were just controllers for other instruments. And, so you started to have things like fully digital keyboards, things that don't make sound at all. Like this, I literally have on my desk, this is a keyboard. It doesn't make any sound at all. You just plug it into your computer and it controls sound on there. Prior to the 80s, stuff like that didn't really exist. And as time even went on from there, you had things like electronic synthesizers and digital audio workstations, which is the thing that I'm most familiar with. And you kind of needed a common standard to be able to control all of these things from one source, because if you buy one product to control the data from another thing and they're just not compatible at all, that's kind of a big problem that needs to be sorted out. So in the early 80s, a couple of different manufacturers got together and they created a common standard that was called the Musical Instrument Digital Interface, which is otherwise known as MIDI. So that is the source of this problem. A couple of questions that kind of need to be answered when it comes to considering what the MIDI standard is going to encompass is who decides what the standard is going to be. Obviously, the people who got together and made it in the first place had their own ideas about what it was going to be, but then it needed to be maintained and developed from there. So who is responsible for deciding what that's going to be? What hardware is required for compliance? In the 80s especially, everything was hardware, and you had to wire everything together with a bunch of cords and cables and stuff. So what things were going to be required to be installed into compliant devices in order for them to actually be connected with that? What format was it going to take? That kind of goes hand in hand with the hardware, but like in order for it to actually work, it needs to be a repeatable protocol like IP that we've been studying in this class. It needs to kind of be a similar format. And IP didn't exist in the 80s. It didn't exist until almost a decade later. So this is kind of actually a precursor to that. How much can the standard be modified for specific applications? Because not every application is going to use the exact same type of data that MIDI was originally designed for. And that type of data is, I'll get to that a little bit later. And then just a little bit more generally, what are the capabilities of MIDI as a format and a protocol? Notice that I'm differentiating a little bit between the format and the protocol. Those terms overlap a little bit. I'll get into a little bit more detail on that. But yeah, that's another question that needs to be asked is what can this protocol actually do for not only for the engineers who designed it, but for musicians who might just want to utilize it with the products that they have. For me, MIDI has been really, really, really important. I direct an a cappella group on campus at UCF. And MIDI as a format has just been really, really important for allowing me to just engage with the software that kind of makes all that stuff happen. You know, it allows amateur musicians like myself to engage with music notation, composition, production software. Because like when I had to bring music to my group, I have to get the music from somewhere, I have to arrange it myself, and then I have to turn that music into whether that be like tracks or whether it be like sheet music that they can look at. And pretty much the only format that you can just put the stuff into that'll be pretty much universally readable by any operating system or any program or anything is MIDI. Because it's a super, super lightweight format. It's super, super digestible for just about any computer. And like that said, it's very, very portable. And the portability of MIDI as a format has caused it to be like pretty much ubiquitous for raw musical information transmission. To give a little bit of an idea of how portable it is. So if you guys have ever just like had a MP3 file on hand, do you guys know, like for just like any old song, do you guys have an idea of how big that file is, like in megabytes or whatever?
Like 2-3 megabytes.
Yeah, like 2-3 megabytes. Sometimes if it's like longer or the compression's not that good, it can be a little bit bigger. But yeah, like 3 megabytes is like a pretty good idea. Usually the MIDI data that contains almost all the same stuff as the MP3 file can be in the range of about 10 kilobytes. So it is a huge, it's like orders of magnitude smaller. And it contains most of the same information that would be needed to recreate the contents of that MP3 file on a different computer. So in the course of the overall project and the literature review, first and foremost, I'm going to try to explain the mechanics and applications of the MIDI standard. So like I was explaining a little bit earlier, I'll give a brief history of the MIDI standard from its inception in the 1980s, because that'll provide a lot of important background as to why they developed it the way they did and what it's become now, because it has continued to be developed since then. And then I'll explain the exact parameters that are established by the MIDI standard. And it'll be a pretty in-depth analysis of the actual bits and bytes that are transmitted when a MIDI data is transmitted. I'll also explain a little bit the relationship between the MIDI standard and the MIDI format that's solely used on computers. That's what I was talking about a little bit before. They're sort of the same thing, but not exactly. They overlap a lot. The MIDI standard, as I'll explain a little bit later, is a hardware, firmware, and software standard. So it covers a lot of different things, but the MIDI format, not so much. The MIDI format is almost solely used on computers. Like you can have just like a MIDI file that just contains raw MIDI information that can be played by a computer. You could also then transmit that through MIDI compliant devices to controllers or synthesizers that can then work with that formatted data. And then finally, I will examine some of the implementation and applications of MIDI in real digital instrument devices like the one I showed you earlier. What I've been able to figure out so far, MIDI is a unidirectional communication standard. That means it only goes in one direction. That'll be really important for looking at some of the hardware compliance stuff that is important to figuring out how it exactly works. That was developed in the early 1980s, like I mentioned earlier, by the joint effort of multiple musical equipment manufacturers. MIDI as a protocol, it contains lightweight music performance data such as pitch, time value, velocity bend, etc. In the larger presentation, I'll give a little bit of background on what those things actually are and how they, and the actual musical significance of them, because obviously for it's musical performance data, so you would want the protocol to contain enough information about a musical performance that it could be, authentically or at least believably recreated by a computer if you were to play it back later. And like I mentioned earlier, MIDI does embody hardware, software, and firmware standards. So the software that's on your computer is almost ubiquitously able to play MIDI data. Pretty much any digital audio workstation that you pull MIDI data into, like GarageBand or Pro Tools or Logic or anything like that, is going to be able to handle MIDI data. It's a hardware standard, so that means that if you get pretty much any digital piano or digital keyboard, it's going to have like a USB MIDI connection on the back that you can put MIDI data into and then connect it to your computer and feed that into just about anything that you would want to do that with. That's a hardware standard. On the device itself, it's going to have firmware standards in order to maintain its compliance with that. But over time, the dedicated MIDI hardware connections have been phased out in favor of USB MIDI connections. MIDI used to be a like actual port. You may or may not have seen it. I don't know if you have not, but that's been phased out over time in terms of just a raw USB connection. And importantly, USB is a bidirectional standard. MIDI is not a bidirectional standard. It is unidirectional. It only goes in one direction. So any two-way communication that's happening between those devices is going to be by USB and not by MIDI. But finally, MIDI 2.0 has been developed, but it hasn't been implemented in any commercially available devices. And I'll do a little bit of analysis into that and what the differences between 2.0 and 1.0 are, because that'll give a lot of insight into why 1.0 is the way it is. This is a pretty standard schedule. Basically, I'll work on it. The only thing that makes this schedule stand out is week 4. I will be collecting some actual musical examples in order to give during the presentation. So just to give good background on what data MIDI is actually like transmitting. And yeah, so it'll be a pretty standard thing. Just to summarize, MIDI is a very powerful protocol that gets used very, very commonly by a lot of different musicians. It's proven really, really useful to me. And it's got some quirks to it, but that kind of make it what it is. And it will, obviously it's in the process of being replaced by other things, but before that happens, I would like to take the time to like kind of do a deep dive into the exact workings of it and kind of share that a little bit. And that's it. So, do you guys have any questions? I definitely went through very, very quickly.
I just have it's an off-topic question.
Okay, I love off-topic.
I'm interested in the silent keyboard that you showed. How exactly does it work?
Oh, so this is just this is what it's called a MIDI controller, and basically you just connect it. So it has you might not even be able to see it, but it has a little. Yeah, you can't really see it on this camera, but it does have a little tiny USB-C connection that you can plug that into your computer. It literally doesn't play any sound. There's no speakers or anything on this thing at all. But if you connect this to your computer, if you have like GarageBand or you have Logic or anything like that, then you can play sound. You can play the keys on this, and it'll produce the sound on the computer. And it's sending that data. It's sending MIDI data through the USB connection in order to play the sounds on the computer.
I see. So it's like a controller situation.
Exactly. Yeah.
Oh, okay. Thank you.
Another question I have.
Yeah.
Give me 1 second. So how do you combat compression when you're trying to send MIDI signals? Is that like an after post-processing thing, or is it before?
Pretty much on MIDI signals, there pretty much is no compression just because it's so lightweight to begin with. Theoretically, if you had like a large collection of MIDI data, then after the fact, you could try to compress that a little bit. But yeah, like at the time when the MIDI data is generated and transmitted, there's pretty much no compression going on with it.
Gotcha. Okay, awesome.
I had one last question. So
okay.
with your literature review, like what are you trying to what are you expecting as outcome? Like, are you trying to improve the ongoing MIDI technology, or like what is the, I guess, end goal?
The end goal kind of is just to kind of, I do have like definitely a very personal interest in like figuring out why and how exactly MIDI works the way it does. And definitely there are a lot of applications to be considered from MIDI just as a standard in electronic music. Because there's kind of like this common discourse among musicians, especially around the time that it was incepted, like, oh, like the computers are taking over, they're gonna like put musicians out of a job. And like some people to this day kind of agree with that, and they like look down on like the ability of musical performances to be encoded into data like that as like kind of a bad thing. And I personally don't think it's a bad thing, and I'd like to kind of get like a better understanding of how it works and like basically verify just for myself that like, no, this is just a process that like musicians use to make music. It's not like computers taking over the world or anything like that. It's just like a thing that exists, and it's a tool to be used essentially.
Impressive. Thank you.
Thank you. All right, let me go ahead and stop sharing my screen.
So awesome. Thank you so much for the presentation. That concludes all of our groups, technically speaking. We do have a lot of leftover time. So I guess, is there any like questions anybody has about the actual presentation or proposal that you guys are confused about? Like you guys having trouble trying to get your proposal ready, your presentation?
Well, first, it was just to pick the topic was challenging. What topic do we want to get into? What do we want to spend our time on? And then once we decided, now let's rush and try to find out all the papers that we could use. So also our challenge was how to organize the material. You know, up to what extent do we talk about what we found? So it wasn't clear much about when does it stop being a proposal and when does it start being more of a presentation.
Yeah, I
It's
agree
kind
with
of
that.
hard to determine. I wish we had like a video sample of a previous presentation so we could use it as a guide, just like the proposal PDF that he sent. It would have been great to have a video sample as well.
It's a good point.
I guess for me, one of the challenges were finding the materials for like the ongoing researches, because since everything is pretty much new that we talked about, like there's not a lot of research going. It's like mainly like people observing and putting in like their hypothesis in a way, right? So like finding actual research papers were difficult. And on top of that, like literature review is supposed to be a summary of like what you read and like say like how it improves this, how it benefits us. In my case, it was like more like it was turning into a research paper kind of, and like actually putting in the data to analyze and see how this specific topic can be formulated, or like how this device can be brought to reality in a way. So
Gotcha. You guys know about the UCF library, right? There's a website and it has like a link where you can search articles, documentation, research. Do you guys know how to navigate to that or no?
I have not used that, no.
Okay. I'm gonna go talk to the professor, see what else we are required to do, and then I'll come back.
Okay, perfect.
I'm gonna end the recording here, technically speaking, but Oscar, you can keep it running if you want, and then I'll be right back.
I'll keep it running.
I got a quick question for the first group if you're interested.
Yeah, sure. We'll try our best to answer.
Just like a power sign question. So what do you guys think if like the goal that the government is putting in right now with 0% carbon dioxide in 2050, do you guys think it's gonna be possible?
Sorry, could you repeat that?
So we know that a lot of company utilities are reaching the goal at 0 carbon dioxide in 2050. You guys think it's like possible?
It's very aggressive predictions for that.
I'm personally.
I personally don't think it's possible. I definitely think we're going to get further. Like I intern at OUC, and they plan on getting rid of their natural gas plant, or sorry, their coal plant, and turning into natural gas. So definitely decreasing. But I'm not personally so confident about the 0 carbon emissions, just because of our reliance on natural gas.
True. And it seems like the renewable energy require a lot of resources such as lands, you know, and yeah, it's not really reliable when the equipment is really reliable on dependent on like the wind or the sun. Let's say in Florida, we have sun all the time, but in around summer, you got a lot of thunderstorm and raining, and how reliable it is, you know, and like on the north, like most of the time it's so overcast, and so I'm not really confident at that goal neither.
Excuse the interruption. Technically speaking, we are done. Everybody has presented, so if you guys want to leave, you can, but if you want to stick around, I'll show you guys the UCF library thing. I don't know, it might help you guys find some research papers. I just thought, you know, I'd help you guys out a little bit if you guys need it.
That would be great.
Yeah, sounds good. Go ahead, please.
Okay, so let me know if you have the screen, if you can see it. Right? You guys can see it? Okay. So UCF login, right? You log into UCF. Let's see, UCF library. So you just type in UCF library on your favorite Google search engine. And I'm trying to find the exact method. It was a long time ago. Let's see. You guys don't know my password, so don't hack me, please. All right. Now, so let's say I want to search IoT integration. Let's try that. These are databases. So let me go back. Where is it? Their UCF library website is kind of annoying, and like there's different ways to access the website, and it's not really clear to get to the main database page. Like right now, I'm in this weird login. No, this is what I'm looking for. Let's try one more time. There it is. I found it. Okay, so let's say I want to search IoT integration, right? And then I want to click research guides. Search. There it is. So now this list gives me like articles that I can access. So study of energy management system and IoT integration in smart grid. That's basically a group 2's entire topic, right? So like, and they give you a full list. You can then filter through the actual results. So if I want to go to this, you sign in. Okay, let me just sign in, which I already am. And the nice thing is that UCF, when you need to log into an institution, it pairs your login with UCF. So you can access a lot of articles that you otherwise wouldn't be able to. Let me see if I can download it. Let me close this. Let me find it. So here it doesn't give me the full text. So sometimes it's a hit and miss, but it's nice to have all the articles in one area. So here it's asking me to redirect to the IEEE Explorer website, but it should give me the full article here soon. So I need to go back and then find the access article. So I believe it's this one. And then I think it was here. Let's try one more time. There it is. And I should have access to the full PDF right here. There it is. So that's the full access. Otherwise, they would ask you to log in and make an account. But yeah, just a little thing to show you guys. Where is it?
Nice. Thank you very much.
Any questions or any doubts about it?
My bad. Could you go back and show me one more time how you got there, please?
Okay. All right. So I'm going to go to Google, reset this, UCF library, go to databases, and then click that, and then search.
Okay. After that, I got it. Thank you so much, bro.
Okay. Awesome. Cool. Thank you, guys.